boom shakalaka. Cause I'm a stats guy and a boom shakalaka. Let's do the same question. We're going to use the same probabilities, asking the same question, but a slightly different method. Believe it or not, we're actually going to end up doing the same math, but it's going to feel different enough that this is called a different method. This is called the counting method. And for the counting method, let's start off with a huge population. In this case, we're talking about women who fit the demographic of having a high risk for breast cancer. So let's start off with 1 million women. Let's see, thousands, million. Yeah, 1 million women. Why so many zeros? Just because I'm hoping to avoid running into decimal places. Now, we want to know if they have breast cancer, if they don't have breast cancer, so we're going to start with how many of these women have breast cancer. Obviously, I can't start with how many of these women will test positive because that depends on whether they have breast cancer or not, which is the same thing that we had to deal with the tree diagram. If I have 1 million women and 1.47% of them have cancer, then I have about 14,000 women with cancer out of this large group, and I'll have 985,000, where's my comma, who do not have cancer. Okay? So that's a way to visualize how frequent or how relative is this cancer. Now, of these women who have cancer, they all come in to get screened. 92% of them is going to say they did have cancer. So I'm going to take 92% of this, which gives me 13,000 women out of this million have come in, they've been tested, the test showed they have cancer, and they really do. This is a good number. These are women who have a problem, and now the doctors can start to discuss treatment, and they're at least aware of it. The other 1,000, they're in trouble. They have cancer, and they don't know it, and that's a bad thing. But this is science. You can't always get everything perfect. We're doing the best we can, all right? You might also notice this is why we started with 1 million, is this doesn't leave us with a decimal place, which just helps with interpretability. On the other side, all these women who do not have cancer, they came in, they of course don't know that they don't have cancer, just like these women didn't know they did have cancer, so they get tested. And we find 22,661, it actually has a 0.9 on it, so 1 million wasn't enough. I should have done 10 million, then I wouldn't hit decimals. But that's how many people are going to have a positive test result. And it's not that much, it's like 3%. There's 962,000 women who go into the doctor does a screen and says, you're okay, and they say, great, thanks, we'll see you next year. So this is by far what usually happens. But let's go back to the question that we want to ask. If the test detects cancer. So not every scenario here is relevant. I'm talking about the people who tested positive. So I want to burn this one and this one. Notice we're doing the same thing we did the tree diagram. Splits into whether you have cancer, splits into was your test positive or negative, and then we say, okay, these are not the scenarios we're talking about. If you tested positive, you're either one of the 13,000 who has cancer, or you're one of the 22,000 who does not have cancer. So what's the probability of having cancer? It's going to be these 13,000 over the total. It'll look like this. The women who have cancer with the test positive divided by the women who tested positive whether they had cancer or not. That's our fraction. We end up getting the exact same probability. In fact, we've actually done the same math. We just multiplied everything by 1 million so that you can see the actual number of women as you go through it. And if this is the way you like to do it, that's great. It doesn't matter. Find what works for you.